Hey guys, you're watching Python tutorials on my YouTube channel, Python for Microscopists. In the last tutorial, we had a quick look at loss functions. And again, for regression, mean squared error is quite common. And for classification, cross entropy is the most common one that you use in deep learning. Now, in this tutorial, let's talk about optimizers. So where do you define an optimizer? Again, model.compile, loss, binary cross entropy in this example. Optimizer, I'm using Adam. Okay, so what does that mean? Well, first of all, an optimizer updates the model in response to the output of loss function. For example, for linear regression, we are trying to minimize the mean squared error by actually placing this line equidistant from all the data points, right? So an optimizer updates the model, okay, in response to this loss function. So the line is moved, and then the mean squared error is calculated. And then the optimizer is like, hey, that's going in the wrong direction. Let's move in this direction. So it moves it slightly and then calculates the mean squared error. And then it's like, oh, that's good. You're going in the right direction. Keep going. So update, move it further, and so on until it finds the minimum. So the optimizer's job is to assist in minimizing this loss function. How does it do that? The easiest way to understand this is by looking at gradient descent. I think this is the granddaddy of all optimizers. This is what how everything revolutionized the deep learning in general. Okay, so what is gradient descent? So first of all, if you look at the loss as a function of weights, again, the weights and biases are the ones that are adjusted after every epoch to make sure we are heading in the right direction. Now, this is a simplistic case showing very nice curve here. So you start with, so let me explain this curve. Initially, you start somewhere with certain weights, okay? That's not optimal. If you're very close to the optimal, then it takes fewer iterations to get there typically. But if you're farther away, let's assume, and then it calculates some loss. Well, this is pretty high. Let me change this. Initially, this data point, the next step may be in this direction. We don't know. The next step may be in this direction, right? And then it calculates the loss and it's like, ho, that's pretty high compared to the last one. So let's go the other direction, other way. And then it goes in this direction. And then it calculates, hey, loss is getting better. Go further. Next step. And the steps here are called the learning rate in general, okay? But this is it. And typically your space here, when you map out the loss versus the weights, it may not be this uniform. You may have like a a valley, but then a small hill and valley and so on. So gradient descent is a way of actually finding this minimum. And think about actually, if I want to find an analogy, I'm not sure how many of you are hikers out there, but think of hiking a hill blindfolded. Well, you go in one direction. You know that you're going up the hill, but your goal is to, let's say, find your way down the hill. So you kind of turn around because you know what the slope is. You feel it in your feet. And here you calculate what the slope is, okay? And then you go in the direction that actually gives you towards the minimum. That's all this is. Now, how big of a step do you take? You can take very big steps. But then sometimes you can feel the terrain if you have smaller steps, right? So these steps are actually called the learning rates. Now, if you look at these two scenarios, on the left-hand side, if the learning rate is very high, you'll get to the minimum very fast. If the learning rate is very high, you see, from here to here to here, it's probably like just 3 epochs or something to get here. But then if the learning rate is very high, you'll never reach the true minimum because the learning rate is too high. You'll never reach this bottom point. On the other hand, if your learning rate is too small, then it will take more epochs, but you'll definitely find a very much closer minima compared to larger learning rate. But the problem is, if this is how your terrain looks like, and then you're blindfolded and you're coming down, then you end up in this valley and you think that you're at a minimum. But in reality, the global minimum is down here. So you may end up at a false minimum, which means your accuracy is not good. Okay, this is not the right answer there. Now, there are certain terms, again, I don't want to get deep into this, but for example, think of this as a rolling ball that's actually coming down the hill, but then as it comes down, it goes here and comes back and then comes back and then settles down at this point, and you're like, okay, that's my minimum. But what if this ball has higher mass, meaning more momentum? So if this ball has more momentum, it comes down here, but then it pushes over this, and then it goes up here, because it has more momentum, and eventually it settles down here. So in deep learning, again, I'm not going to talk about this much because this is a hyperparameter. We are not going to tune much, but momentum is something that you can define, which exactly does what I just mentioned. It speeds up, first of all, this process, this learning process, and moreover, it ensures that you're not at these false minima or pseudo minima. Okay, so this is your optimizer. Now, gradient descent is an older version, but a new version, again, there are many of these. I'm going to talk about only one, Adam, because this is the one that is very common nowadays. Okay, so Adam optimizer, here is the link to the original paper. Very insightful if you can read this whole thing. Okay, there's a lot about this. I'll just summarize a few things. First of all, Adam stands for adaptive moment estimation. Okay, and I should actually go back. One thing I should highlight here, you see this learning rate. For gradient descent, that learning rate is constant. Okay, for Adam, it's not constant, and I believe it's part of the summary that the authors actually put together. First of all, Adam is computationally efficient, apparently compared to the other approaches. Little memory requirements, and well suited for problems that are large. Okay, for large data sets in terms of data or the number of parameters that you are that need tuning. And it's appropriate for problems with noisy or sparse gradients, and hyperparameters have intuitive. I just copied and pasted these things. If they don't make sense, that's okay. Noisy and sparse gradients is, as the name suggests, you look at the gradients and they're like kind of noisy or very sparse. The best thing I like about Adam, let me put it this way, is I do not have to adjust any of these hyperparameters, like these learning rates and a few other things. And I'll show you the default values. Almost everyone uses default values. The TensorFlow, when I say everyone, all libraries, like Keras, for example, they all use whatever got published in the original paper. So this makes your life easy. You don't have to play with a whole bunch of things. Someone else did the work kind of for you, okay? So here is the graph out of the original training paper, where they kind of compared this with a few of the other ones, and you can kind of see the training cost for Adam, as a function of iterations, is minimum compared to all the other approaches. Okay, so I trust this, and for almost all the time, I actually use Adam for most applications. Now, like I mentioned, most popular libraries use the default hyperparameters. I keep doing this, sorry. Default hyperparameters from the original paper, and here are the hyperparameters that we use. Meaning, when you select Adam, these are all the default parameters that get actually used. Okay, so this is optimizer, and again, in the next tutorial, I am going to talk about metrics, and so that should finish at least our understanding of model.compile, and let's also see if there are any parameters under model.fit that need a bit more explanation, and then let's also cover that in one of the upcoming tutorials. So thank you very much for your attention, and let's actually meet again in the next tutorial to talk about metrics.